Math Blast 33, Tuesday. I can determine multiples. Matthew and Elmer were playing a game on a numbered game board. A section of their game is on the left. In the game, players have to cover numbers that are multiples of both 5 and 6. Circle all the numbers on this section that are multiples of both 5 and 6. So first I'm going to determine the numbers that are multiples of 5. Numbers that I get when I skip count by 5 would be considered multiples of 5. Those numbers are the products, the answers we get when we take 5 and multiply by something else. So 5, 10, 15, 20, 25, 30, 35 is not on our game board, 40. Okay, so on the game board, I have put a 5 in each square that has a number that's a multiple of 5. You'll notice also that multiples of 5 are all numbers that end in a 0 or a 5. That's a divisibility rule itself. As for 6s, we're going to now find the numbers on the game board that are multiples of 6. I'll skip count by 6s again. Or I should say 6s this time. 6, 12, 18, 24, 30, 36, and then 42 would be off the game board. So now I can take a look at the game board and see which numbers, or number in this case, has 5 and 6 both in the box. So I'm going to circle 30. That's the only number on the game board that would be considered a multiple of both 5 and 6. I can generate and analyze patterns. What would be the 21st shape of this pattern? So when I take a look at the pattern, I can see that the pattern is created with 3 terms here. We have an oval, this 12-sided shape, which is called a dodecagon, and another dodecagon. Or some of you might look at that and just say, hey, that looks like a plus sign, and that's okay here. But I'm going to say oval, dodecagon, dodecagon before it repeats, and we then again have an oval, dodecagon, dodecagon. So I know that there are 3 terms in each part of the pattern. With the number being 21 that I'm looking for, the 21st shape, I know that 7 groups of 3 would give me 21 because 7 times 3 is 21. So it would be that 3rd shape in the 7th group of the pattern that would be the 21st shape. So I know that the 3rd shape's always going to be this dodecagon. And so I can say here dodecagon. Or we also could just sketch it out here the best you can. It's not going to be perfect, and that's okay. All right, and then how can you determine the 21st shape without drawing onto the pattern? Well, I could say that we can say 7 times 3 equals 21, and we know that that 21st shape is going to be the 3rd shape in the 7th group of the pattern. Would be the 21st shape. All right, next, I understand place value relations. Write the value of the 7 in each number. 7,361, the 7 has a value of 7,000. 5,781, the 7 has a value of 700. Compare the value of the 7 in each number above. I can say that 7,000 is 10 times as many as 700. I know if I had 700 on a place value chart, each of those digits would shift to the left 1 time to become 7,000. And on a place value chart, each time our digits shift to the left, we are multiplying by 10. I can solve word problems involving addition and subtraction of fractions. There are 2 pies on the table that are the same size. The first pie has 7/8 eaten. The second pie has 3/8 eaten. How much pie is left? Show your thinking using a fraction model or an equation. Since we have 2 pies on the table that are the same size, I'm going to draw 2 circles here to represent those pies. I know my units that I'm dealing with are eighths because the denominators in my fractions are 8. So I'm going to break each one of the pies into 8 equal parts. Now, in the word problem there, we learned that in the first pie, 7/8 was eaten. So I'm going to cross off 7 of the 8 pieces. I can show that in an equation. 8/8 is the whole pie, and if 7/8 was eaten, we're going to subtract 7/8, and we would have 1/8 left. In the second pie, again, 8/8 would be the whole pie, and it said 3/8 was eaten. So we're going to put an X on 3 of the 8 pieces and subtract those, 3/8. And we would end up with 5/8 left. Now we haven't answered the question yet because it says how much pie is left. So from the whole thing there, if 1/8 is left in the first pie and 5/8 is left in the second pie, then 6/8 would be left. And you can make a statement there answering the question, 6/8 of the pie is left. I can solve problems involving measurement. The avocados Kristen bought weighed 1 kilogram, 631 grams. The watermelon she bought weighed 752 grams more than the avocados. How much did the avocados and the watermelon weigh together? So here I'm going to represent first the avocados. The avocados were 1 kilogram, 631 grams. The watermelon, I'm going to put an A here for avocados. The watermelon weighed what the avocados did, that 1 kilogram, 631 grams, plus 752 grams, because it said 752 grams more. So now we can determine what the weight of the watermelon was. And so I can do that by adding these. I can say, well, 1 kilogram is 1,000 grams. So 1,631 grams was the avocado. And if we add on the 752 grams more that the watermelon was, then that's going to tell us what that watermelon's weight is. Grams will be the units, and when I add my like units here, I find that we get 2,383 grams. Now again, that's just the weight of the watermelon. The question is, how much did the avocados and watermelon weigh together? And so that's what I'm trying to determine here. I'm going to put these together, and I will find that 1,631 grams for the avocado plus the 2,383 grams for the watermelon will give me the total weight. Again, I'm going to add like units, and I get 4,114 grams. So I can make a quick statement here. 4,114 grams is the weight of the avocados and watermelon. Together. Just taking our question and rewording it here with our answer in there to make a statement. That's all for today, math friends.